Silence. That's the first thing you notice. No wind, no rain, no birds, no traffic. Just the low, mechanical hum of machinery and the slow drip of water somewhere in the darkness ahead of you. You are standing at the face of a drill site, 70 meters below the surface of the Yellow Sea. Around you, reinforced concrete walls, still wet from the last round of waterproofing injections. Fluorescent lights stretch into the distance like a runway that never ends. Above you, the ocean. Thousands of tons of salt water pressing down on the rock between you and the open sea. And your job, the job of 6,000 workers who came here every single day for 5 years, is to keep drilling forward. Welcome to one of the most extraordinary engineering projects in human history, the Qingdao-Jiaozhou Bay Tunnel. 8.5 kilometers of road tunnel bored directly beneath the Yellow Sea, connecting the port city of Qingdao on China's eastern coast to the Huangdao Economic Development Zone on the opposite shore. When it opened to traffic in June of 2011, it immediately became the longest undersea road tunnel on the surface of the planet. And it still holds that record today. Now, before we get into how China actually built this thing and the engineering decisions that made it possible, let's talk about why it needed to exist in the first place. Jiaozhou Bay sits between Qingdao and Huangdao like a wide, flat wall. For decades, the only way across was by ferry, a journey that could take well over an hour depending on weather and traffic, or a road that looped nearly 50 kilometers around the entire bay. For a city growing as fast as Qingdao was growing, that was unacceptable. Something had to change. To understand why building a tunnel here was so difficult, you have to understand what Jiaozhou Bay actually is. It's a shallow, semi-enclosed coastal bay, roughly 370 square kilometers of open water, formed over millions of years by the shifting of tectonic plates along China's eastern seaboard. That geological history is important, because the rock beneath the bay isn't the solid, predictable granite you'd want to tunnel through. It's fractured, inconsistent, riddled with natural fault lines and underground water channels that don't show up neatly on any geological survey. In other words, it's exactly the kind of geology that makes engineers nervous. And there's another problem. The bay is a working waterway. Container ships, fishing vessels, naval vessels, they move through Jiaozhou Bay constantly. Any structure crossing the water couldn't interfere with that traffic. A bridge was briefly considered, but in a region that sees typhoons, heavy fog, and freezing conditions in winter, a bridge over an active shipping lane was a safety nightmare. The only real option was to go under the shipping lanes, under the seafloor, under the ocean itself. The tunnel was the only answer. The question was whether it was actually possible. In 2006, the Chinese government officially approved the Qingdao-Jiaozhou Bay Tunnel project. The budget, approximately 4.9 billion Chinese yuan, equivalent to around 1.5 billion US dollars at the time. The target completion date, 5 years. For context, the Channel Tunnel between England and France, a comparable undersea tunnel project, took 7 years to build, cost nearly double, and was financed by a consortium of international banks that required decades to pay back. China was proposing to build something similar, faster, and entirely with domestic financing, domestic engineering expertise, and domestic labor. The international engineering community paid attention. Some were skeptical, others were quietly fascinated. At the time, China had been on an infrastructure building spree unlike anything the modern world had seen. New highways, new airports, new high-speed rail lines appearing seemingly overnight. But an undersea tunnel of this scale was different. This wasn't just laying track across open plains. This was drilling blind, beneath the ocean, through unstable rock. This was a test of something deeper than just concrete and steel. Let's talk about what drilling an undersea tunnel actually involves, because it's more complicated than most people realize. When you're tunneling underground on land, your primary enemies are gravity, ground pressure, and groundwater. You deal with those using a combination of mechanical excavation, explosive charges, and structural lining systems that stabilize the tunnel as you advance. Now take all of that. and add a pressurized ocean above your head. Every crack in the rock above the tunnel is a potential pathway for seawater. Every fault line is a zone where the rock could shift, settle, or collapse under the combined weight of the ocean and the surrounding geology. At the deepest point of the Qingdao Tunnel, roughly 70 meters below sea level, the hydrostatic pressure from the water column above is approximately 7 atmospheres. That's 7 times the pressure you experience at the surface. The engineering team faced a choice between 2 primary excavation methods. The first was a tunnel boring machine, a massive rotating drill that grinds through rock mechanically. The second was drill and blast, a more traditional approach using explosive charges to shatter the rock face, followed by mechanical removal and structural lining. They chose drill and blast, and the reason why reveals a lot about the intelligence behind this project. Tunnel boring machines are marvels of engineering. They're fast, consistent, and relatively safe in predictable geology. But they have a critical weakness. They are not designed for fractured, inconsistent rock. In rock that shifts unexpectedly, rock with fault lines running through it, a TBM can get stuck. Or worse, it can breach an underground water channel and flood the entire work zone in minutes. Given the geological surveys of the Jiaozhou seafloor, the engineering team determined that drill and blast was the safer, more controllable option. Here's how it works in practice. Workers advance to the rock face. They drill a precise pattern of holes, sometimes dozens in a single pass, into the rock using pneumatic drills. Explosive charges are placed into those holes at carefully calculated intervals. The crew retreats. The charges detonate in a controlled sequence, not all at once, but in a timed cascade that shatters the rock while minimizing vibration and the risk of collapsing the surrounding structure. Then the debris is cleared. The newly exposed rock face is examined, sprayed with a fast-setting shotcrete to stabilize it, and the waterproofing system is applied before any lining concrete is poured. Then the process starts over. Advance. Drill. Blast. Clear. Seal. Line. Advance. Drill. Blast. Clear. Seal. Line. Every single day, for 5 years. Here's something most people don't know about the Qingdao Tunnel. You're not driving through one tunnel. You're driving through one of 3. The project was actually constructed as 3 parallel bores, 2 main traffic tunnels, each carrying 3 lanes of traffic in opposite directions, and a central service tunnel running between them. That middle tunnel isn't for cars. It's for people. Emergency exits from the main tubes connect to the service tunnel at regular intervals, giving workers and, in an emergency, drivers a safe escape route if something goes wrong in either main bore. The service tunnel also houses the ventilation systems, the drainage infrastructure, and the mechanical systems that keep the whole operation running 24 hours a day. Those 3 bores had to be excavated simultaneously, advancing in parallel, with thick concrete walls separating them at every point. Every decision made in one bore had structural consequences for the other 2. The coordination required was extraordinary. Of all the engineering challenges on this project, the most persistent, the one that never went away, was water. During excavation, the team encountered multiple unexpected underground water channels feeding directly from the bay. These weren't small seeps. Some of them flowed at rates that required industrial pumping systems operating continuously just to keep workers safe. The waterproofing system they developed has multiple redundant layers. First, after each blast and debris clear, a shotcrete lining is applied directly to the bare rock, sealing small cracks and providing an immediate stabilizing skin on the excavation. Then, a full continuous waterproofing membrane is installed across the entire inner surface. This is a synthetic material, dense, pressure-resistant, essentially wrapping the inside of the tunnel like a sealed envelope. Finally, the structural concrete lining, the layer you see when you drive through, is cast in place on top of all of it. At every joint between concrete sections, specialized pressure-resistant seals were installed to prevent any migration of water between panels. And still, to this day, the tunnel pumps out a constant flow of groundwater every 24 hours. That's not a failure. That's just physics. Numbers can only tell you so much about a project like this. At its peak, the Qingdao Tunnel employed over 6,000 workers simultaneously. 3 rotating shifts. Around the clock. No weekends. No holidays. These workers operated in some of the most demanding conditions in industrial construction. Underground environments are physically punishing. The air quality is managed but never perfect. The noise from drilling and blasting is continuous. The psychological weight of working beneath the ocean, knowing what's above you, is something most people will never fully understand. And yet, the workers kept coming back. The project maintained one of the lowest accident rates of any major undersea infrastructure project in modern history. That wasn't accidental. The engineering team embedded a safety culture into every level of the operation, from the most senior project directors to the workers handling explosive charges at the rock face. Every worker on the Qingdao project was trained not just in their own task, but in how their task connected to the safety of every person around them. That kind of systemic thinking doesn't show up in the engineering reports, but it's what made this project possible. One of the most critical and least talked about innovations on this project was the real-time monitoring system embedded throughout the structure during construction. Hundreds of sensors were installed directly into the rock and the concrete lining as work advanced. These sensors measured structural stress, water pressure, rock displacement, and temperature continuously, feeding data in real time to surface control rooms staffed around the clock by structural engineers. If any sensor showed a reading outside the expected parameters, work in that section stopped immediately. A dedicated inspection team was dispatched. The anomaly was investigated, documented, and resolved before any work could resume. This monitoring infrastructure wasn't removed when the tunnel opened. It's still active today. Every movement, every pressure reading, every structural change in the Qingdao Tunnel is being tracked and recorded in real time. In effect, the tunnel is its own permanent research station, continuously teaching engineers how undersea structures actually behave over time. On June 30th, 2011, the Qingdao Jiaozhou Bay Tunnel opened to the public. The first cars drove through at midnight. Not a ceremony, just traffic. Just the ordinary movement of people who had places to be. A journey that had taken over an hour by ferry now took less than 10 minutes by car. The project had been completed on schedule, within budget, without a single structural catastrophic failure during construction. The international engineering press took notice immediately. Reports from tunneling organizations in Europe, Japan, and the United States described the Qingdao project in terms that don't get used often in technical literature. Remarkable, unprecedented, a new benchmark. And China, characteristically, moved on, not to celebrate, but to start the next project, and the one after that. Because for China, this wasn't a finish line. It was a warm-up. The techniques developed on the Qingdao Jiaozhou Bay Tunnel didn't stay in China. The waterproofing membrane systems, the real-time sensor monitoring approach, the modified drill and blast sequencing for fractured submarine geology, all of it has since been adapted and applied to undersea tunnel projects across Southeast Asia, the Middle East, and Africa. Chinese engineering firms that built their expertise on this project are now among the most sought-after infrastructure contractors on Earth. Meanwhile, China itself kept building. The Hong Kong-Macau Bridge, the longest sea crossing ever constructed, includes an undersea tunnel segment allowing container ships to pass overhead through an active shipping lane, using methods refined at Jiaozhou Bay. The knowledge base built beneath that bay in 5 years has shaped underwater infrastructure development globally for the decade that followed. That's what happens when you attempt something genuinely difficult. The lessons don't just improve your next project. They change the entire field. Every day, tens of thousands of people drive through the Qingdao Jiaozhou Bay Tunnel. They're on their phones. They're listening to music. They're thinking about dinner, or their workday, or what they need to pick up from the store. They are not thinking about the 70 meters of ocean above their heads. They are not thinking about the 6,000 workers who spent 5 years in the dark to give them this road. They are not thinking about the engineers who built a waterproofing system that has to hold perfectly every single moment of every single day. And that, more than any statistic or record or engineering milestone, is the real measure of what was accomplished here. The best infrastructure becomes invisible. It becomes normal. It becomes something people forget was ever impossible. Somewhere right now, a team of engineers is looking at a body of water on a map and asking the only question that matters. What if we just went underneath?